All right, I'm going to go through this multiple choice questions from test C, and then in another recording I'll go through the free response questions. This is for part 6. This is on quantitative inference. So the first question is about the t-distribution. Now we've had a whole bunch of questions about these, and practice questions. T-distributions are mound-shaped and symmetric, and they're more spread out. And as degrees of freedom increase, the variance of t-distributions becomes smaller. So in this particular multiple choice question, 1 is true, 2 is true, and 3 is false. Now, let's look at the previous questions, because there's been 3 of these so far. So let's look at the previous ones. Let me go up here. I'm going to make this a little smaller so we can see it better. Okay, so let's go up. It's always been question 1. Which statement correctly compares t-distributions to the normal distribution? Okay, 1 is true. 2, t-distributions have less spread. That's false. They have more spread. 3, as t-distributions of freedom increase, as degrees of freedom increase, the variance of t-distributions becomes smaller. That's true. Okay, why? Because the degree of freedom is simply the sample size minus 1. And let's get a little worksheet up here. Let's make this smaller. It's not the way to do it. I'm going to drag this over. Okay, let's bring it over here. All right, so the standard error for sampling distributions for quantitative data. Here, let's make this a little heavier. Let's make it medium. Okay, so the standard error equals the standard deviation of the sample divided by the square root of n. Now df, degrees of freedom, equals n minus 1. Now, pardon me. So, as the standard error gets smaller, then the distribution is going to get smaller as well. Okay, here's the size of the standard error. It's like a ruler. It's like as if the length of a yard got smaller. Okay, the standard error is a unit of measurement. It gets smaller. Standard error gets smaller as n increases because of the inverse relationship. Okay, namely, as n gets bigger, the whole thing is going to get smaller. All right, so for instance, the standard error equals, let's suppose the standard deviation is 10 and the sample size is 4. So the standard error is going to equal 5. Now the standard error is going to equal 10 over, let's say, the sample size is 9. It'll equal 10 over 3, or 3 2/3. So the standard error is getting smaller, and which is simply how spread out the graph is. The standard error is going to equal, let's suppose the standard deviation of the sample remains 10, but now the sample size is 16. Okay, so now it's going to be 10 over 4, which is 2.5, and so on. Okay, if the sample size is 25, then it's 10 over 25. Now it's going to equal 10 over 5, which is 2. So as n increases, as the sample size increases, or degrees of freedom, because the sample size is increasing, degrees of freedom is increasing, the standard error of the statistic is decreasing, which means that, what does that mean? It means that the distribution, the t-distribution, is getting more compact. Now, here, let me pause this for a second because I want to show you a demonstration of this on the internet. So I'm going to pause this for... Well, I can't get the internet to work right now, so I'll have to show you with my drawing pictures. Let me... So, suppose this is the normal distribution. Now, by the normal distribution is meant the following. Each one of these distances along the x-axis, they're supposed to be the same. This is a standard deviation. Okay. Okay, so this is between -1 and 1 standard deviations from the center of the normal distribution is 34% of the population. 34% here, 34% here. In terms of whatever, from the point of view of whatever statistic you're thinking about. And so 68% is between -1 and 1. Now between -2 and 2, there's another 13.5 here, 13.5 here, for a total of 95%. That's in between 2 standard deviations. And then there's 2.35 here and 2.35 here for from -3 to +3 standard deviations. There's 99.7% of the population is found from the point of view of whatever the parameter of interest is, whatever it is you're measuring, either height or weight, or the proportion of the population that's in favor of a certain thing or whatever. And then 0.015 is what's left in each tail. Now, so that's the normal distribution. That's what's meant by the normal distribution. I'm going to draw here again a picture of the normal distribution, like this. Okay. It's mound-shaped. Now, this doesn't look very mound-shaped and symmetric. Okay. Now, underneath it, I'm going to draw a t-distribution. And let's say this has 2 degrees of freedom, 2 DOF. Okay, it's going to look approximately like this. It's going to be shorter and more spread out. Why? Because the sample size is so small. So it's going to have a bigger standard deviation, so then it's going to be more spread out. Okay, now, suppose we have a t-distribution of 10 degrees of freedom. Then it will look like this. The tail will be shorter, and the mound will be taller, but it still won't be normal. Okay, it's less spread out. Why? Because it has a bigger sample size, so a smaller standard deviation. So it's less spread out than a sample of size 2, but it is more spread out than the normal distribution. Here, let me black is normal. Okay, and then let's go with, I don't know, what other colors do I got? Let's green. I got green. So let's do a t-distribution that of 20 degrees of freedom. Okay. The tail will be still fatter than the normal. It'll be less fat than the degrees of freedom of 10. It'll be a little bit taller. Okay. But the tail is still more spread out than the normal distribution. Okay, now what's the last one? What's the last color I got here? Let's see. I'll go with gold, I guess. Okay, so we'll say a t-distribution, and let's call it 100 degrees of freedom. Okay. Now, the tail the tail will be skinnier. This is going to be pretty much indistinguishable from the normal distribution. Okay, why? Because the sample size is so big. So in each case, now this is, like I said, this is, I'm just trying to show you what's going on here. As the sample size gets bigger, it gets less spread out, so the tails get less fat, if you will. And the mound, the center of the distribution, gets taller. Okay, why? Because the sample size keeps decreasing, making the standard deviation of the sampling distribution smaller. So the sampling distribution is less spread out. Okay? That's how it works. And so that pretty much answers all these questions. So let's go back to our document. So that was question number 1. T-distributions are mounds shaped and symmetric. That's always true. T-distributions have less spread. No. They have more spread. Okay? They're more spread out. That's what the fat tails mean. The phrase fat tails means it's more spread out. Okay? As degrees of freedom increase, the variance of t-distributions becomes smaller. And that's true, okay, because the standard error is getting smaller and smaller. Now let's go up to that last test, test A, and let's discuss that question here from the same point of view. Okay, let's go through all this stuff here. Okay. It'll be question 1 again. Which of the following is true? Unimodal, symmetric, and bell-shaped. Those are all true. Those all mean this, the same thing. Fatter tails, true. As degrees of freedom increase, the T-models look more and more like the normal. That is true, as I'm trying to show you here with my lousy little drawing. Okay? As the degrees of freedom increase, the graph, okay, the distribution, the main thing is, the graph is going to look very much like a normal distribution, but the distribution itself is going to be normal. That is, it's going to become closer and closer to 34, 34, 13 and a half, 13 and a half, 2.35 in each, as you're going from standard deviations to the left or standard deviations to the right. Okay, now let's go back to the test. And let's get back down to, well, you know what? Let's keep doing this. Let's go back to A and question number 2. Okay, and then maybe we'll go through and we'll discuss how every one of these questions and do the ones that are similar. Okay, 98% confidence interval for the mean hours per week spent studying was 1317. Okay, now let's review what a confidence interval is. What does it mean? If we say we have 98% confidence, we are 98% confident that the true population parameter for what it is we're studying, in this case, that the true mean hours per week spent studying by college students is between 13 and 17. And that's it. Okay? Now, the first statement is deceptive. It says there's a 98% chance. We are this 98%. The confidence interval is not a statement of probability. It's a statement of confidence. Period. Okay, so we're not saying there's a 98% probability that the mean hours per week spent studying by college students between 13. We are saying we are 98% confident. So 1 is wrong. 2, 98%. Okay, 2 is a statement about the population, the whole population. 98% of them study between 13 and 17 hours a week. The confidence interval is not a statement about the whole population. It's a statement about a particular population parameter. And it's a statement about what the parameter is. In this case, it's the average number of hours studied. It's not a statement at all about a proportion of the population. So 2 is wrong. 3. Students average between 13 and 17 hours. Okay. Students average between 13 and 17 hours per week studying on 98% of the weeks. Okay. Now 3 started out okay. They average between 13 and 17 hours. Okay, that is part of the correct statement of a confidence interval. But now it's gotten back to a statement about when they do this. Okay, it's another statement about the behavior of the students. Okay, that's not what it's about. It's about an average, a population parameter. It's not about how the students behave on 98% of the time or 15% of the time or whatever. Okay, so 3 is wrong. None of these are correct. Now, let's go down to the second multiple choice question and see how that compares. Okay, all right, they found a 95%, this is the marketing company, 95% confidence interval, mean length of time 23-27, which is true. Okay, again, we see the same kind of error. It's a statement about the population. 95% of the commercials are between 23 and 27 seconds. Wrong. That's not what a confidence interval means. Confidence interval is a statement of confidence about the population parameter. In this case, mean length of a commercial between 23 and 27 seconds. B, 95% of all, no, it's another statement about the population. 95% of all the commercials. Forget it. B is out. C, commercials average. Now we're talking about, okay, it starts out okay, just like in the previous problem, between 23 and 27 seconds, long on 95% of the days. Now we're throwing in this time thing. That's not what it's about. D, 95% of all samples, all right, would show mean commercial length. Okay, now this, what is this saying? If you took 1 billion samples, 95% of them would have a confidence interval between 23 and 27 seconds. Now think about that. That is extremely unlikely. Okay? Especially, we're measuring seconds here. Okay? It's possible that there would be very few or none. Okay? So D is a confusion about the statement of level of confidence, which states that 95% of all samples would produce a confidence interval that contains the true mean length of the commercials aired daily. Okay? But there is nothing in the statement about the meaning of the level of confidence, or 95% confidence, which implies that the confidence interval is the same as the one that you're working on right now. Okay, the probability of that confidence interval occurring again is low, very low. Okay, E, we are 95% sure or confident that the mean commercial length is between 23 and 27 seconds. Okay, that is correct. Okay, that is the correct phrasing for a confidence interval. Now let's go on to C and see what test C has for this question. All right, a random sample, 120. Okay, that is, okay, that's, oh no, I'm sorry, it's question 2. Okay. 23 and 27. Second, did we already go over this? I think we did. We're 95% sure. E is correct. D is wrong for all the reasons that we talked about before. C, B, A, all wrong. E is correct. Okay. Let's go back up to test A. All right. We got a whole bunch of these. Okay. All right. So, which of the following formula gives a 99% confidence interval for the mean GPA of the professor's students? Okay. Now, we know that the standard error for the sampling distribution has got to be the standard deviation over the square root of n. Okay, so every answer has 0.534. Okay, so they all have the right standard deviation, but only 3 of them have the square root of 15. The other 2 have the square root of 14, which is the degrees of freedom. So D and E are out. Okay, for A, B, and C, all 3 of them have 3.01. So we can't make any distinction on that basis. Let's see. We are doing a 99% confidence. Now, my guess is that, let's see, probably C is 99% confidence for the normal distribution, and I would guess that B is the 99% confidence for 14 degrees of freedom, and I would guess that A is 99% confidence for 15 degrees of freedom. So I would think that B is the right answer without even figuring anything out. Let's calculate. We're going to use inverse T. So let's calculate the degrees of freedom, and let's calculate the what is T star. So we're going to use second and vars, and then inverse T number 4, or use the program if you have it. If you don't, we'll use the formula sheet. Now we're going to do 0.995, and the degrees of freedom is 14. Okay, so 2.97 is B. Now I figured B was right, because I figured since A has a lower T star, I figured that was probably calculated using 15 degrees of freedom instead of 14. And I would bet anything that C is the 99% level of confidence using the normal distribution. So anyway, B is the right answer. Now let's use the formula sheet to find this. So I'm going to open up a test. Bear with me for a second here. So I'll go to the statistics exams, and let's page down. Okay, so we're looking for the T distribution. I'm going to make this, let's pull this up to 100%. Okay, now 99%. Okay, that means a tail probability. And if we can go down, if you're not sure, let's go down to the bottom. Okay, so here's 99% confidence level. Okay, so let's go up 99 until we get to 14. All right, now 14 is 2 above, so 2.98 or 2.97. Now, what did they use in the answer? Let's go back to the question here. 2.977. Okay, well, that's the answer we have. That's what we got from the table. Let's look at that again. Let's look at it again. 2.977. Fine. So that's exactly the same number you would have gotten from the table. You can see you got 14 degrees of freedom in the column. That is 99%. Notice in the tail, it's 0.005. Okay, now let's look at the other questions that are similar to this. Let's go to part B. Okay, let's go a little too far. Okay, so here we go. Okay, here's the same thing. All right. Now we're going to eliminate D and E because they use the degrees of freedom in the denominator instead of the sample size. So it's got to be A, B, or C. And so now let's look at, this is 95% confidence. We can tell right away that A is using the normal, is using the Z star for 95%, 1.96, 1.97 or whatever. Okay, so we know that A is out. And again, I'm using my same sort of rule of thumb here, that whichever of these T stars is smaller was probably made with the degrees of freedom of 10. Whichever one is bigger was probably made with the degrees of freedom of 9, which will be the right answer. All right, so, but let's settle it with the calculator. I'm going to do we'll do this again. Okay, now this time we're going to put in 0.975, half the distance to the goal line, and degrees of freedom is going to be 9 because sample size is 10. And let's see what we get. All right, so 2.262. Okay, this is a bigger T star than this, which means that this was probably made with 9 degrees of freedom and this was made with 10. Now let's just check that real quick since we're sort of trying to learn here about what's going on. So, yeah, see, this one was made with 10 degrees of freedom. So here's where the mistake is. The person used as their degrees of freedom the sample size, not the sample size minus 1. Okay, easy mistake to make. And in a multiple choice, unfortunately, it's 100% fatal. Okay, let's check the next question that's like this. Okay, let's get back. Just to make sure we're covering all 3 tests. And here's okay, here they are. Okay. And we're doing a 95% confidence interval. Okay, we see right away that A is wrong because it's using the 1.96 Z star, which is actually the Z star instead of the T star. It's using what we'd use if we had a normal distribution, if we were doing a confidence interval for proportions. Okay? D and E are both wrong because they have the wrong, they're using the degrees of freedom instead of the sample size in the denominator of the standard error. So what do we got? We got B and C, and again, I'm just doing the same thing over and over again. Whichever one has the larger standard error is probably correct, is probably using 9 degrees of freedom instead of 10. The bigger the degrees of freedom, the smaller will be the standard error. Okay, well, smaller will be T star. All right, so, and in fact, they're the exact same numbers as we did in the previous problem, 2.262 and 2.228. So we can see that C is going to be the correct answer. All right, let's go back up. Let's do the next thing, which is a proportion problem. Let's go back up to the top. Okay. it doesn't, I thought there was a proportion problem in here somewhere. It doesn't seem to be in the first test. Yeah, here it is. Okay. All right, so it's number 7 in this case. 13 of 52 and 11 of 88 cars fail the emissions test. Assuming these vehicles are representative cars, what is the standard error of the percentage of cars and trucks that are not in compliance with air? Okay. Of the difference. Okay, so we're doing now. Here, let's get my notepad out here. Let's get this thing going. I'm gonna make this smaller. Okay, so let's make it black. Okay, the standard error of p hat delta equals the square root of p hat sub 1 q hat sub 1 over n sub 1 plus p hat sub 2 q hat sub 2 over n sub 2. So it's going to, p hat, doesn't matter which order you do this in, okay, sub 1 is going to equal 13 out of 52, which is, if you are a card player or whatever, or if you're any good at math, you're going to recognize right away is 1/4. So q hat sub 1 is 3/4. So this is going to really help us out a lot. And then p hat sub 2 is 11 out of 88, which is 1/7, okay, which is 0.14, let's see, 147, what is it? 1428527. Okay, 1428. So let's call it 0.143. And then 1428. So 0.143. So 6/7 equals 0.857. Let's see. 10, yeah, okay. All right. So let's make ourselves a little extra space here. So the standard error of p hat delta equals the square root of 0.25 times 0.75 divided by 52 plus 0.143 times 0.857 divided by 88. Okay, now let's drag this over here. I think that's right. Okay. Oh, let's drag it without making it. Okay, now so you just got to do this in a calculator a second. Okay, 0.25 times. Now, since you're doing straight division and multiplication, and the denominator has only one term in it, you don't need parentheses. 0.14 times. Okay, so let's double check. 0.25 times 0.75 divided by, oh, I left out a number here. 0.52 plus 0.143 times 0.857 divided by 88. Okay, 0.0706. Now, any of the answers resemble this? 0.070, yeah, 0.070. Now, pretty sure it's the right answer. I just want to double check, and this is the only answer I really want to check right now. Let's just double check. 7 is D. Yeah, okay. Now, let's check the other tests. The other tests have proportions problems on them. Okay, number 3 is a proportion problem. Random sample 120 classrooms, found that 70%. 70% of them had been cleaned properly with standard error of the sample proportion. Okay, let's get our little notepad up here. Okay, we'll drag this over so we can say we're doing 120 and 0.7. Okay, so the standard error of p hat, because we only have one sample here, equals the square root of p hat q hat over n, which is going to equal the square root of 0.3 times 0.7 over 120, and we get the calculator in a second. Square root of 0.3 times 0.7 divided by 120. Double check 0.3 times 0.7 divided by 120. Okay, 0.042, and that's the right answer. Okay, and then there's one more. Let's go look at those in the third one. Okay. It's the exact same problem, only in this case 30% get jobs. You're going to have the exact same result, 0.042. Okay, let's go on to the next problem. Let's go up to A and see what they have as the next question. All right, Professor, mean age, after collecting data from the random sample of the students, the professor tested hypothesis. It's the alternative, not equal to 0. The p-value is 0.003, which is true. Okay. The p-value is the probability that your sample statistic is true, assuming that the null hypothesis is true. Okay? So, A, there's a 0.03 chance that the mean ages for the men and women. No. That's a statement about the population. You guys coming back in? Okay. So it has nothing to, it's not a statement about the sample. So A is wrong. There's a 0.03 chance that the mean ages for the men and women are different. Okay. Another statement about the population, not about the sample. Wrong. Okay, C. Now we got to think about this one. It's very unlikely that the professor would see results like this. The results meaning his sample statistics. If the mean age in women were equal to the age of men was equal to the mean age of women. Okay, now this is the right answer. Now let's decode this a little bit, because I was telling you the meaning of the p-value is the probability of the sample statistic occurring randomly, and I didn't say randomly, I always got to say that, randomly, assuming the null hypothesis is true. Now the null hypothesis is the mean age of women is equal to the mean age of women. Okay, that's the if. Okay, this if thing here. If the mean age of women are equal to the mean age of men, that's the assumption of the null hypothesis. Okay, and with a p-value of 0.3%, 0.003, that means it is very unlikely that the sample statistics would occur if the null hypothesis were true. C is correct. D, there's a 0.3 chance that another sample will give these same results. Just has nothing to do with the definition of the p-value. There's a 99.7 chance. That's again nothing about the p-value. Okay. 5. Now let's see what other questions are about the p-value that are similar. Okay, but they're going to have this kind of repetitious quality to them. But we can talk about them. Okay. Okay. All right. Another p-value, p equals 0.22, which is true. All right. People using ergonomic keyboards get 22% more. Okay, whoa. Nothing to do with p-value, probability of the sample statistic occurring randomly, assuming that the null hypothesis is true. A has nothing to do with that. Okay, it's a statement about the population. There's a 22% chance that people using ergonomic keyboards type more words. Another statement about the population, nothing about the sample. There's a 22% chance there's really no difference in typing speed. Another statement about the population, nothing about the sample. There's a 22% chance another experiment. Okay, nothing about the sample. The p-value has nothing about other experiments. Okay, it's none of those. Final multiple choice test. Okay. Group of chickens, p-value of 0.22, eggs, you can just read it, okay? Chickens will lay 0.22 more eggs. P-value, the probability of the sample statistic occurring randomly, assuming that the null hypothesis is true. A is totally wrong. Statement about the population. B, statement about the population. C, statement about the population. D, another statement about an other experiment has nothing to do with this. Totally wrong. Okay. Let's go back to the first thing here. A. Okay, here we're going to get number 5. Absorption rates. They run a small experiment to test against the alternative test that there's no difference against the alternative that there is a difference. Now, which of the following would be a type 1 error? What is a type 1 error? You reject the null when the null is true. Okay? You reject the null when the null is true. Deciding the absorption rates are different. That would be rejecting the null when in fact they are not. A is the correct answer. B, deciding the absorption rates are different when in fact they are. That would be a correct conclusion. That would not be an error. C, deciding that the absorption rates are the same when in fact they are not. That would be deciding that they are the same when in fact they are not. That would be a type 2 error. Okay, that would be failure to reject the null when the null is not true. Deciding the absorption rates are the same when in fact they are. Okay, that would be a correct conclusion. Okay, that would not be an error. The researcher cannot make a type 1 error since he has run an experiment. No, you can, if you have an hypothesis, you can make a type 1 error. Okay, so the correct answer was, I believe it was A. Deciding the absorption rates are different when in fact they're not. A type 1 error, reject the null when the null is true. Type 2 error, fail to reject the null when the null is false. Okay, you can only make a type 1 error if the null is true. You can only make a type 2 error if the null is false. Okay, let's go down to and see how the same question is asked on the next test. Okay. Let's see. Where do they do it? Type error. Trainer's purpose. Okay, here it is. Okay, old new equals 0. Alternative is greater than 0. Old minus new is greater than 0. Which would be a type 2 error? Okay, let's review. Type 1 error. Reject the null when the null is true. Okay, in this case, you decide that the old is more expensive than the new when in fact it is not. Deciding that the new lenses are cheaper when in fact they really are. Okay, that would be not an error. Okay, that would be a successful. That would be a correct conclusion. Okay. B, deciding that the new lenses are cheaper when in fact they are not. That is a type 1 error. Okay, the null hypothesis is that the new lenses are not cheaper. Okay, that they cost the same. Okay. If you decide that the new lenses are cheaper, then you are rejecting the null, and you are deciding there's evidence for the alternative hypothesis when in fact the null hypothesis is true. That is the type 1 error. C, they're asking us type 2. Okay, deciding the new lenses are not really cheaper when in fact they are, that's a type 2. Okay, so failure to reject the null when the null is false is a type 2 error. You can only make a type 2 error when the null is false. Deciding the new lenses are not really cheaper when in fact they are not, that is not an error. Applying these results to all contact lenses, old and new, I'm not sure what that means, but it certainly is not a type 2 error. Okay, so C is a type 2 error, deciding that new lenses are not really cheaper when in fact they are. Okay, all right. Which test was this? This was test. Okay, here's test C. All right, what do they ask us here? Where is the... I guess they don't ask the error here. Let's see. Okay, and we're going to go back up to the top. It doesn't look like they asked that type of question here. All right. Okay, so let's see, where were we? Okay. We're just going to do one of these since it's very straightforward. They want to know the pooled estimate of the standard deviation. So you're going to go to stat, and you're going to go to tests, and you're going to go to a 2-sample t-test, number 4, and you're going to arrow over to stats and hit enter. And then the data in this table is related by row. Okay? Now x bar is the mean, and s sub x is the standard deviation. So I'm going to put in 32, and the standard deviation that goes with that is 5, and the sample size that goes with it, that's n sub 1, is 25. And then I'm going to go to the second standard mean, which is 30, and a standard deviation of 6, and a mean of 20. Now let's double check. 32, 5, and 25, 36, and 20. Hit enter. Okay, I'm not running the test, so I don't care which test I use. Not equal to, two-tailed, tail left, tail right, doesn't matter. Pooled, yes. I arrow over and hit enter. This is the only time you're ever going to pool is to get this goofy statistic. All right, this was the test we're doing. This is the null hypothesis that they're not equal. Here's the t-score, the p-value, degrees of freedom. Okay, here's the mean, 31, 30. This is all given. And here is the pooled standard deviation, 5.46. Okay, that's all I care about. All right, we're not going to do any others of these. This is the only one we're going to do. Okay, 7. Oh, no, we did this one. Okay. 8. Okay. SAT test site. Students taking volunteer to inhale supplemental oxygen. Okay. Others were given normal test results of 42 of 66 students who breathed oxygen improved their SAT scores compared to only 35 of 63 students who did not get the oxygen. Which procedure should we use to see if the breathing extra oxygen helped the test takers think more clearly? We should use a 2-proportion z-test. Okay, we got why these students are independent of each other. It's not a before and after test, or the same students took the test before. Some got oxygen and then some did not. So anyway, and the students are randomly assigned to treatments. So it's 2-proportion z-test. Okay. 9. The survey asks people on what percent of days you get more than 30 minutes of vigorous exercise. Using their responses, we want to estimate the difference in exercise frequency between men and women. We should use a okay, this is a confusing question, okay, because they're talking about what percent of days, but it's asked from, it's not like we have a whole group of people and then we have a proportion from this group of people, like 30%, we pulled a whole bunch of women and 30% of them exercise every day or something like that. Rather, we're going to have a different percent from many different people. On what percent of days do you get more than 30 minutes of vigorous exercise? Okay, so even though we're talking percentages, it's really quantitative data. All right, and that we're definitely comparing men and women, so it's not matched. So E is out. Okay, so we're not talking proportions. We definitely have 2 samples, so C and A are out. Why? We have a sample of men and a sample of women. They're not matched because they're independent of each other. Okay, we're not using the same people to do this. We're not doing it before and after or anything like that. And since we're talking about quantitative data and not proportions, rather we're taking a whole bunch of proportions and we're treating them as numbers, the correct answer here is D, a two-sample t interval. I may as well finish off now with 10. Okay, and we have a whole bunch of questions like this. All right. So, two agronomists analyzed the same data, testing the same null hypothesis about the proportion of tomato plants suffering from blight. One rejected the hypothesis, but the other did not. Assuming neither made a mistake in calculations, which of these possible explanations could account for this discrepancy? Okay. One agronomist wrote a one-tailed alternative hypothesis, but the other used two tails. All right, that could definitely do it. Okay, that could definitely do it. Now let's explain that, because this, if you can just skip the, take the scrubber and move it ahead or something if you don't want to listen to this. Okay. Let me scroll down here, down. New page. Why won't this go down? Here. Sometimes this is, sorry about this. This is getting to me a little, okay. All right, now I can scroll down, make a new page. All right. Suppose alpha equals 0.05. All right. So if H sub A is P sub 1 minus P sub 2 is greater than 0, and because that's a one-tailed test, okay, and suppose the p-value equals 0.03 for that test. Okay, so in other words, the probability of that difference occurring, assuming that there is no difference, is 3%. Okay, you would reject the null if alpha is 0.05 because 0.03 is less than 0.05. But if H sub A is P sub 1 minus P sub 2, or P1, I'm sorry, we should be talking, P sub 1. P sub 1 minus P sub 2 is not equal to 0. Okay, then you're testing the probability of either tail. So there's 0.03 left in both tails. It's a two-tailed test. Okay. You're testing the absolute value of the z-score. Whatever the z-score is, it corresponds to a p-value of 0.03. You're testing it on the right and on the left. So 0.03 plus 0.03 equals 0.06, which is greater than 0.05. So with a two-tailed test and a p-value for a one-tailed test of 0.03, you fail to reject if you're running a two-tailed test. Okay, so one is true. Okay, they wrote identical hypotheses. Okay, they wrote identical hypotheses. All right, so here's scientist 1, and his alpha is 0.01, and here's scientist 2, and his alpha is 0.05. Well, if the p-value equals 0.03, scientist 1 will fail to reject, but scientist 2 will reject. Okay, the p-value is in between the two. Okay, and do scientists use different alphas? They most certainly do. Okay, 3, they wrote identical, so 2 is true. If the one who rejected the null used a higher, no, wait a minute, hold on. The one who rejected the null used a higher, yeah, that's right. Okay. They wrote identical hypotheses, but the one who rejected the null used a lower alpha level. Okay, if your alpha level is lower, then you're going to fail to reject. Okay, so here's the guy. Here's the p-value. Okay, this guy used a higher alpha, and he rejected. Reject. Okay, and that's what they're saying in 2. The one who rejected the null used a higher alpha level. Okay, higher alpha means he had lower standards. Okay, he required fewer standard deviations or standard errors to reach significance. Okay, the guy with an alpha level of 0.01 has higher standards. He requires more z-scores to reach significance. Okay, so he used a lower alpha and he rejected. So 3 is wrong. It's 1 or 2. All right, so we're done with test A. Let's go down and finish off test B, as long as we're at it. Okay, we did all of these. We did that. Okay, 6. Let's talk about 6. He checks all the family, the researcher checks all the families in the school, and then he wants to do a t-distribution. Why is that not appropriate? Because he's doing a census. You only do inference if you're trying to find out about a population from a sample. He didn't use a sample, he checked out everybody, which is fine. Nothing wrong with that. Okay, 7. Trainers need to estimate the level of fat in athletes to estimate good health. Initial tests were based on a small sample. Now the trainers double the sample size for a follow-up test. Now, the main purpose of the larger group is to reduce response bias. Okay, what is response bias? Response bias is when you ask leading questions. Okay, so if I don't see where response bias could even come into this. Okay, I mean they're measuring levels of fat. Okay, there's no way you can ask a leading question in interrogating somebody about how much fat is in their body. You use technical equipment for that. Okay, so response bias is out the window. Okay, you only have response bias when you ask a leading question like, do you favor, stronger gun laws to reduce the slaughter from handguns or whatever, or are you against gun laws that restrict our Second Amendment, all of that kind of thing. Okay, B, decrease the variability of the population. Okay, let's get one thing really, 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 really clear here. Okay, you're taking your little sample, is changing the population. Okay. You don't decrease the variability. The only thing you can change is your sample. Okay? Reduce non-response bias. Okay? Doubling the sample is not going to reduce that. Non-response bias is when you put out a questionnaire or something and not enough people answer it. Okay? But you've got the sample. I don't think there's any problem with people not responding to it. Okay, increasing sample size to reduce confounding due to other variables. Increasing sample size doesn't make confounding go away. Confounding is eliminated by blocking and by control of all of the variables in the experiment. Okay, has nothing to do with sample size. E, decrease the standard deviation of the sampling model. That is completely true. That's mathematically true. Sample size gets bigger, standard deviation gets smaller. Okay, we already talked about that. Okay, standard error equals either p hat, q hat, square root p hat over n. N gets bigger, standard error gets smaller, or standard error equals the standard deviation of the sample divided by the square root of n. N gets bigger, standard error gets smaller. Period. Okay? All right. Based on data from 2 large samples, 2 students test hypothesis of equality, alpha equals 0.02, one used a one-tailed test, rejected the null, the other used a two-tailed test. We've talked about this. Okay, Which of these might have been the calculated value of t? Okay, well, two very large independent samples. What does that mean? The distribution is normal. Normal distribution. Okay, very large samples, doesn't matter if it's quantitative data. You have a very large sample, you have a normal distribution. Okay, so what you're going to do, second, vars, normal CDF, you're going to plug in the numbers, and you want to find a p-value that is going to be, for a one-tailed test, will be less than 0.02, but for a two-tailed test, will be bigger. Okay? So I'm going to start with I think 1.22 and 1.55 are too small. I'll try 1.88, comma 99. Okay. Now that's 0.03. Now even on a one-tailed test, okay, that will fail to reject the null. Okay, so 1.88 produces a p. I'm effectively, even though it's a t-score, I'm treating it like a z-score. Okay, like it's a normal distribution. That would fail to reject the null with alpha equals 0.02. Okay, so I'm going to go to D. I'm going to try 2.22. So I'm going to do second, vars, normal CDF, number 2, and I'm going to put 2.22, comma 99, close parenthesis. I hit enter. Okay, now, all right, this is good. 0.013 is the p-value. Remember, this is a one-tailed test, so the output of normal CDF is the p-value. 0.013 is less than 0.02, so this would reject the null. But that's for a one-tailed test. But for a two-tailed test, it would be 0.026. In other words, 2 times this number. That would, adding the right tail and the left tail together, I'd be 0.0. So for a two-tailed test, it would fail to reject. Okay? So the correct answer is D. All right? All right. We're not going to do now. We already did those. Okay? Just review, recall the previous problem. Okay, so this is done. Okay? So let's go down to the next test. Let's finish this off. This kind of lengthy thing here. You're probably getting tired of all of this. Okay, so what do we haven't done from C? Investigators, equal amounts of chickens, wildlife, red squirrels. I think we talked about the squirrels. No, we did the squirrels. Okay. We talked about this college seniors, investigators, and we talked about the p-value, and let's see. Internet search gives us all scores. We create a 95% confidence interval. Okay. The procedure is not appropriate. Why? We checked all the scores in the history of the tournament. That's a census. Okay? That's a great thing to do. It's really cool. Use the internet. Get all the data. Okay? You don't have to do all this inference. Okay? That's how we're going to do things more and more. All right, great. 7. Okay, initial test based on double the sample size. Okay, here we are. Sample size thing again. Okay? The main purpose of larger sample is to reduce confounding due to other variables. Now, increasing sample size doesn't eliminate other variables. They're still there. Okay, you just have a bigger sample. Reduce response bias. We already talked about that. Can't reduce response bias. Okay, plus how would levels of contaminants be? How would response bias come in there anyway? Since it usually has to do with how people answer questions. Decrease the variability in the population. We've already talked about this. You would be a pretty clever customer if you know how to change the variability in a population. Okay. Reduce non-response bias. Okay. We are taking contaminants from food products. I don't think we have to worry about the food products not responding to our tests. They don't have free will. They can't hang up their phone. They can't ignore you. Okay? These are objects which we have complete control over. Okay? The only possible correct answer is A, decrease the standard deviation of the sampling model. as n gets bigger, the standard deviation gets smaller. Okay? Based on one-tailed, okay, here's the one-tailed test, two-tailed thing. Okay, and this time alpha is 0.05. Okay? So let's go through this again. Now, two very large independent samples. Okay? Doesn't matter. We're using a t, but it doesn't matter. We're gonna treat these answers as if they were z-scores with the normal distribution. So I'm going to do second vars. This time I'm thinking 1.88 is going to work. So I'll do normal CDF. Why? Because alpha is 0.05. 1.88. Okay. Oops, I forgot the 99. Here's a second. Come on. Come on. Okay, so that's 0.03. So 0.03 is less than 0.05. So with a one-tailed test, I would reject the null. I multiply it by 2 to make it into a two-tailed p-value. It's 0.06. Aha, bigger than 0.05. So a two-tailed test would fail to reject. So the correct answer is 1.88. 9 we've already done. Okay, 10, the totally new question. All right. Now, let's talk about game B. I think pretty much everybody gets, but let's talk about it anyway. You want to get between 45 and 55% heads. Now we're talking about a confidence interval, and it's clear that the more, we've already talked about this, that the bigger the number of throws that you throw are, in this case 50, okay, then the smaller the standard deviation, which means the closer you are going to be to the population mean, which is 0.5. Okay? So you clearly, to win game B, you want to throw as many times as possible to make the smallest possible standard error, to make the smallest possible confidence interval, which means your chances of getting between 45 and 55 are going to be greater and greater. Okay? In fact, what is the standard error for? So let's think about this for a minute. It would be second square root. Okay. 0.5 times 0.5 divided by 50. Okay, so that's 0.07. All right, so it's still pretty big. So it's going to be 0.05 plus 0.07. So that's 52. Well, we're not multiplying it. You know, what level of confidence do we want? You know, so the confidence interval is going to be pretty big. Let's say we want we multiply this by 1.96 times 1.96. Okay, so it's 13% plus or minus from 0.5. So 0.5, let's call it, it's almost 14 plus 0.14. Okay, and then 0.5 minus 0.14. All right, so the confidence interval for 50 throws is still pretty big, considerably wider than 45% and 55%. Okay, but anyway, that's the best you can do. All right, but you definitely want, you know, if you could have 1,000 throws or something, that would be much better. Now, what about getting exactly 50% heads? Okay, now this is an entirely different consideration, and for this we need to talk about something we haven't talked about in a while, which is binom PDF. In other words, what is the probability of an exact binomial event occurring? Because this is binomial. Okay, the throws are independent. Okay, it's the probability doesn't change. You're throwing a coin, and they're independent. They don't change, and it's a yes or no. You only got two possible events: heads or tails. Anyway, so it's a Bernoulli situation. So let's go to stat and then test, and let's go to binom let's see, second, I should be doing second of ours, I'm sorry. I did this earlier, okay. Okay, binom PDF. Why? Because we're calculating the probability of exactly 5. Okay? So let's say we were throwing the coins 10 times. So it's NPX. So we're going to throw the coin 10 times. Probability of a head is 0.5. And we're hoping for 5 heads. Okay? All right. So that's about 1/4 probability. Now let's do the same thing for 20. I think if you use your common sense here, you're going to realize the more times you throw, the less likely it is that you're going to get exactly 50%. But if you can't figure it out, if you're like me, you're not all that smart and stuff, then you can do a little bit of an experiment here and just plug in the numbers. So for 20 coins, the probability of getting 10 heads is only 17% as opposed to for 10. Now let's look at 100. What's the probability for 100? So we'll do second and enter. And let's do 100 coins. Oops. So 100 with a probability of success of 0.5, and we want 50 successes. Exactly 50. Oh, what did I do wrong? Oh, I forgot the comma. Okay, so second, insert comma. All right. Okay, now it's really low. It's 8%. Okay, so anyway, the probability of a particular event, a particular Bernoulli event occurring, is going of a single Bernoulli event occurring is going to go down as the number of trials increases. But the probability of your sample statistic being between a couple of percentages, in other words, we're talking about landing, but what we're talking about is a confidence interval. The probability of being in that interval is going to increase as the number of throws goes up. So if you get A, you have to do what, 20 or 50? 20 for A and 50 for B. And that's the end of this rather long-winded, over an hour. Wow, look at that.